how goes everything?
Not really positive what we should be looking for number 3. I don't know where to begin on that one. On the homework file.
Is this a homework question?
Yeah.
Awesome.
I feel like it has something to do with the power set, but that doesn't really make sense in the context of what we've been learning.
Alright, let's see what it says.
Change the power set or something.
Number 3, a function maps from 1, 2, 3 through n to 0, 1. How many possible functions are there?
So this would be, what they're asking for is something like f of 1 equals 0, f of 2 equals 1, that kind of thing?
Yeah.
Okay. So that's right.
It would be n times 2, wouldn't it?
So why?
We have a product rule, you have choices 1 through n for task 1,
Oh, I see how this
and
works.
then 0 and 1 for task 2.
So what's task 1 in words?
Choose a number between 1 and n.
Integer, yes.
An integer before.
So one time all of them to 0, another time all of them to 1.
So choose an integer from 1 to n and what?
And assign it a value 0 or 1.
Okay. And then what's the second task?
That was the second task, I think. Assign it a value of 0 or 1.
Okay. And then what?
Well, I mean, if we look at it from right there, you can see where she gets that. We've got n possibilities for the first task,
Mm-hmm.
with the first time round. Second
Mhm.
time it'll be, I guess, n minus 1 or something.
Mm-hmm.
And then the second task only has 2 possibilities. And then, like you said, the product rule.
Okay.
I could see how that would work.
The difficulty with that is, suppose I pick the number 1 and I assign it a value, and I pick the number 2 and I assign it a value, and so on. I could instead have said, okay, first I'm going to pick the number 2 and assign it a value, then the number 1 and assign it a value, and then the number 3 and 4 and 5 and so on. And I might end up with exactly the same function. And if I just count all those different ways of doing those tasks, I'm going to be counting functions more than once. Does that make sense?
Vaguely.
So what is a function from this set to this? What do we mean by that mathematically or in words?
We just studied this for the exam last time.
Yeah.
Well, it means that for the first set, it maps to something in the second set.
Right. So each thing in the first set maps to something in the second set.
Subjective and injective, which one would that be? That would be
I
subjective.
don't think it's,
It's not
It doesn't need to be
specified.
either.
It might or might not be either of those.
All that has to happen is all n in the first set have to map to one of the numbers in the second set.
Correct.
And they
F
could
of
all
1
map to 0, right?
has to go somewhere. F
Yeah.
of 2 has to go somewhere. F of n has to go somewhere.
And since it doesn't have to be surjective or injective, they could all map to 0.
They could all map to 0. Yeah.
Okay.
If n was 1, if I was just mapping from the singleton set of 1 to there, then it's not going to be surjective either. And if n is bigger than 2, it's not going to be injective because I'm going to have things mapping. We could pigeonhole it if we wanted. But to define this function f, we need to define what each of these values maps to, right? And if we break it into those tasks, this task can be accomplished two ways. We can map 1 to 0, or we can map to 1. This can be accomplished two ways, and so on. And so you've got a total of 2 to the n ways to decide what all of those map to. If we think of our task as first picking a number here, we have n ways to do that, and we have 2 ways to get over here. That's going to give us 2n ways to do this once, and then the next time we're going to have 2 times n minus 1.
And that's going to give us 2 to the n as that follows through.
I don't think so, but it's going to include duplicates. And if you factor those out, I think you're going to find the number of ways that you could have done this first task, the number of ways you could have chosen, the number of orders in which you could have chosen these things. I think that's going to turn out to be n factorial. So this whole thing, which is 2 to the n times n factorial, if you divide out the number of ways that you can end up defining the same function, I think that's going to divide out an n factorial, and you're going to be left with 2 to the n. And we're going to talk about combinations, and combinations are basically ignoring order. So breaking that into an n task and a 2 task, that would get you to the number of combinations. And there's a question on 2.
Yeah, I was wondering if we can use all the letters, all 26 of them, or we have just specific 4 letters, which we are reserving some of them.
You can use any of the 26 letters available, uppercase or lowercase, subject to these constraints. So in A, you're only allowed to have 4 uppercase letters. So it could be any 4 from A through Z, and you're allowed repeats. And the way you choose your letters, the order definitely matters here, because the first letter, second letter, if you swap those, it's a different password. So we want to pay attention to order here, so it should be product sum rules. So we were talking about permutations. So what was an R permutation of N objects?
Are you saying, like, what does it equal
What did it mean?
It's like
Oh,
you've got.
sorry, go.
You can go ahead if you want.
Oh, I was just gonna say, the R would be like the number of things in that permutation, and then an object is the total number of objects you have.
Okay, so
If you had a deck of cards,
Yeah.
you could say that you had a 5 permutation of, what would it be, 52?
52, yeah.
Yeah.
That'd be a
It has
Like
to
in
be
a
point.
poker hand or something.
and it has to be ordered,
Oh,
Okay.
right.
right? So it's an ordered arrangement. a set of n items. And we had a shorthand for it.
It was, P, yeah, and comma R.
Okay. And what was our formula for that?
N factorial over n minus r factorial.
Alright, so we can find the value of this. Yeah,
Do we ever care about an unordered set of R objects?
we do. We will in about 2 minutes.
Oh, okay.
Maybe 1 minute.
Got that sixth sense
So
for
it's
where we're
timely.
going.
That would be the commutation, wouldn't
That would be combinations, yeah.
Literally a poker hand, it doesn't matter what
Right,
letters
right.
it's in when it's dealt.
That's what I was wondering. It seems odd that that's the order.
So if your alphabet is the letters A through G, and you want to know how many different words you can form that have exactly 5 letters, the order matters. So that's just a number of ways we can pick 5 things from a set of 7 letters.
So no repeats then?
You're allowed repeats. Oh, let's see. I have to be careful with that.
it? Yeah, we talked about repeating.
We haven't talked about repeating. Right, it's an arrangement, so that's no repeats.
An arrangement means no repeats?
Oh, so they're all distinct?
Yeah, you just,
Oh, I didn't know
The only thing that's coming to mind is flowers, and I know that's not valid.
that works.
It does?
Yeah,
Wow. Well, you can have an arrangement of flowers with more than one of the same type.
but you take your 6 daisies and your 2 roses and your tulip, and you're arranging them, right? So which do I put where? So yeah, an arrangement is taking a set of things and putting them in order.
But we're not saying one tulip, one rose. We're only saying one of that exact tulip, right? Is that what you're saying?
So here's a permutation of this, right?
Yeah.
Right, here's a different permutation,
Right.
because it's a different order. Right, that's not a valid permutation of those
Okay.
objects. And the reason we get this formula, well, if it's just an n permutation, it's because there's n ways to pick the first object, and that leaves you with n minus 1 ways to pick the second object, and then n minus 2, and so on. That's where your n factorial is coming from. So once you pick an object, it's no longer a candidate. Suppose I want to find permutations of this containing 5 letters, but I require that my resulting 5-letter word includes A followed by B followed by C. find that.
Wouldn't it just be the 2 remaining options that
Yes.
we would work with?
Yeah.
So we could rephrase this as a permutation of these 5 things. And we're required to include this one. And then we have 4 others to choose from. But this is quickly leading us to the question of when we don't care about order. So a combination is an unordered collection. So like a poker hand, you don't care about the order in which the cards are drawn off the top of the deck. So an R combination of N objects is just an unordered collection of R objects.
So are we still avoiding repeats here, or no?
Yes.
Yes, okay.
Yeah, we're selecting things from a set of objects.
Right, so you can
So
select
if I
the same
have
object
2
from-
letter A's in there, I can pick 2 letter A's.
Right,
But I can't pick one object multiple times. So for example, pick 3 volunteers from a set of 4. I'm going to volunteer 3 people to work the problem on the board. And it doesn't matter the order in which I choose people, right? The question is, how many different sets of 3 volunteers can we get? So how many ways can we pick 3 people out of 4? Let's call your people A, B, C, D.
Oh, I see.
And
I
then
think-
4, 3, 2, 4 times 3, 4 times 2.
I think we can start with the, what we were just using, the R from N, I don't remember what you called that specifically.
Isn't it 4n?
Permutations.
Start with that and then divide out. That doesn't seem like it's working.
Yeah, that's gonna work.
It's on the right track.
We could take the number of ordered permutations and then somehow divide out the different orderings.
The amount of times that ordering occurred.
Yeah, so for example, if you have 4 people, A, B, C, D, and you want to pick 3 people from there, there's A, B, C, A, B, D, A, C, D, B, C, D, and there's B, A, C, and there's B, A, D, and there's C, A, D, and there's C, B, D, and there's A, C, B, and so on. Let me know if I repeat myself. I'm not going to do this, it's going to be another 12. But what I'm doing to write these down, I'm rearranging these. Right, so here I swap the first 2, here I swap the last 2, I could swap the first and last.
Is this just gonna be a simple product rule?
Basically.
Because the order doesn't matter, it's just, I'm going to be picking one letter from A, B, C, D, and then my second choice, I'm gonna be picking one letter from A, B, C, D, except for I can't choose the second letter, or I can't choose the first letter again.
Mhm.
So it's just a simple product rule.
Well, that looks like a simple product rule. But again, we're actually going to be counting identical solutions more than once. If I pick the letter A, and then B, and then C, that's going to be exactly the same as if I pick the letter B, and then A, and then C. That's the same group of 3 people. So this is part of our answer. But the other part, actually that's not part, we're only picking 3, that's if we're picking 4. But we need to account for the fact that we have multiplicities in the set that we picked if we pay attention to ordering. So here's a different way to look at this. If you're picking 3 people from the group, then there's one person you're not picking. How many ways can we exclude one person from our group?
4.
4. How many ways can we pick 3 people? 4. So that's a backhanded way of getting to the answer. But we'd like to generalize that so we don't have to be tricky. So that's the number of ordered ways that we can pick R objects from a set of N. And this order, this order, this order, we want to treat those as all the same. How many different ways, once we have a solution of N objects, how many ways can we order that? How many ways can you rearrange a set of R objects?
In terms of R factorial,
Mm-hmm.
number of ways you can.
Right, that's just P of R comma R. That's what a permutation is. It's an ordered arrangement of objects. So the number of ways we can order R objects is just R factorial. P of R comma R. So this is the number of permutations of R objects from a set of N. But we're counting each different arrangement as a unique combination. So if we divide by the number of ways that we can order these objects, we get the number of unordered combinations. And so this is combinations. It's the number of combinations, and we write this with this shorthand. And this is basically number of permutations divided by number of well, it's P of R comma R, number of ways to arrange R objects from a set of R. So if you're picking 3 people from a set of 4, that's just the number of 3 combinations of 4 objects, which is 4 factorial over 3 factorial times 1 factorial, which is just the number of poker hands, that's 52.5. Which is just that, yeah.
Is that the simplest way we can get it? Because that seems really complex for what it's actually doing.
I don't know a simpler way,
That is the simplest one.
I'm pretty sure that's simplified, yeah.
unless
I've
you're,
seen that before. You can't like factor out of like a
not in general.
factor out of factorial.
I mean, we know r is less than or equal to n, so we could factor this out of this, or we could factor this out of this. But then you write it with a bunch of things with dot, dot, dot in between. So this is actually a little more succinct. But if you do this for a living, right, then this is the simpler way to write it.
And then you just punch it into the calculator and call it.
Yeah.
And that 2 million.
Yeah, so it's still a good set of combinations. So how many 8-bit numbers include exactly 3 ones in their binary representation?
Say the combination of 3 or 8 things 3 at a time.
Sure, we can basically say, pick the position 1 through 8 of each one. So we've got 3 1-bits in our number. We can pick the first bit to be in either position 1, 2, 3, 4, 5, 6, 7, or 8. The second bit can be in position 1, 2, 3, 4, 5, 6, 7, or 8, but not the same position because it's the second bit. And the third can be in one of the remaining positions. So we're taking combinations of the numbers 1 through 8, and we're looking for a combination of 3 of those. And we don't care about the order. So that's just number of 3 combinations of 8 things. For example, that binary number corresponds to 1 to 8. If we start with the rightmost bit and we call that 1, we move our way over. And if I had picked my 3 numbers to be 2, 1, and 8, that's exactly the same binary number. That still says we have a 1 in bit positions 2, 1, and 8, and 0 everywhere else. So this is picking 3 numbers out of 8 where we don't care about the order. So that's just 3 combinations out of 8.
So would it do factorials with this?
With a calculator?
Yeah.
Yeah,
Oh, I'm sure.
It's in the
That probably does, like
Yeah.
permutations and combinations.
It's go into, push the math button and go to the menu that says probability, factorials and permutations and combinations. Probably unicorns too.
NP, go over to PRB,
Oh.
and then NP, order, so probably N,
Oh,
so
that is
permutations
what
of
I
R.
was looking at that before.
Yeah.
We're on a radio station, the video game character.
NPR.
That can't be right. Oh. Wow, this looks familiar.
Yeah.
that maybe I've seen some or
Something about a triangle.
Yeah.
what kind of triangle is it?
SpongeBob.
Again?
So there's powers of x plus 1. And you normally see this done with like a plus b raised to a power. I'm going to simplify it a little. X plus 1, we're just looking at powers of that. And the question is, how do we write down the coefficients for x plus 1 to the n? Using Pascal's triangle. How do you multiply polynomials? You FOIL, right? First, outer, inner, last. And if you have 3 things to multiply, well, let's do a few. Let's do 5. Okay, we know that we're going to get an x to the 5th in there, right? And from experience, everything else is going to be less than or equal to 5. And our answer is probably going to be something in this form, some 5th degree polynomial. And we're basically going to pick one of these terms, multiply by one of these terms, multiply by one of these terms, and so on. And we're going to do that in all possible ways. Right, that's what FOIL is. Right, first we do these, then we do these, then we do these, and then we do these. You find all the possible ways of multiplying a piece of one expression by a piece of another expression. If we think about that up here, we're going to choose one of these objects, either x or 1. We're going to choose one of these, x or 1 of these, one of these, one of these. We're going to multiply them. And that's going to get added to our final answer. So our final answer is going to be all the different ways that we can choose one of the things from each of these terms and multiply them together, all added together. So how many ways can I pick something from each of these so that I end up with something times x to the 5th? There's only one way. I've got to pick the x, the x, the x, the x, and the x. Because if I pick the x and the 1 and the x and the x and the x, I'm not going to get x to the 5th. I'm going to get x to the 4th. And if I pick 2 of the 1s, I'm going to get x cubed. So the only way I can get an x to the 5th is to pick all of these. And that's the only term that's going to contribute to x to the 5th. So this is going to be a 1. But what about the coefficient for x to the 4th? How many ways can I choose things from these 5 sets so that I end up with x to the 4th?
4 times, I don't know.
I could choose these x's in this one. That's going to give me x to the 4th. I could choose these x's in this one. I could choose these x's and this one. But whatever I do, I need to choose 4 x's out of this set of 5 binomials. In other words, I have to choose exactly 4 of these 5 binomials and say I'm going to pick the x from that one. So I've got 5 binomials and I'm trying to pick 4 of them. That's just 5, 4. And the order doesn't matter, right? I could pick this one, this one, this one, and this one, or I could pick this one, this one, this one, and this one. That's the same x to the 4th. So it's a combination, and this is actually 5, 4. And if I want to get x cubed, I've got to pick the x from exactly 3 of these 5 binomials. Because if I pick x, 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 that's going to multiply to x cubed. And the other terms will multiply to 1. So the number of ways that I can pick exactly 3 of these, that's just 5, 3. And to pick two x's, that's 5, 2, and 1x is 5, 1, and 0 x's is 5, 0. There's only one way I can pick no x's from any of these, and that's just to pick the one from each of them. And I can generalize this one. The way to pick 5 x's out of 5 binomials, that's just 5, 5. So these combinations actually give us the coefficients for a binomial expansion. And so we started talking about Pascal's triangle. And this is just an expansion where we take each number as the sum of the numbers above it. And so on. I can fit one more. There we go. And these turn out to be just the number of combinations of column objects out of row objects. So let's see if I have a green marker. And so among other things, you can use Pascal's triangle to write down coefficients for binomial expansions, which was what I did a few minutes ago. And we mentioned some of the quirky properties that you find with this. This is your set of sums of consecutive integers. I don't know why exactly. The sum of each row is a power of 2. So that's 16. The next one's 32, and so on. And that's not as difficult to imagine since you're adding the elements above it twice. That's for each number in the next row. I still don't know a good reason, but if you're in a prime row, every number is a multiple of that prime. So 3 is prime, those are multiples of 3. 5 is prime, those are multiples of 5. 7 is prime, these are all multiples of 7. But that's not the case for
Is that
non-prime rows. Yeah, cool. Pretty sure. And I did think about it briefly once when I woke up in the middle of the night, and I think it comes down to residue classes again. If you keep adding things together, modulo a prime, you can start with any number, and if you keep adding, you'll always end up covering all the possibilities. Right? You can, what we call, generate the set of integers modulo a prime from any of the numbers other than 0. And somehow I think that's what's kicking in here. Whereas if you're not prime, like if you're modulo 6 and you start with a 2, you get 2, 4, 0, and you never get to the odd numbers. Somehow I think that kicks in. But there's an even weirder one.
But wait, there's more.
Wait, there's more. Let's see if I can do this.
That's not promising.
so if we think of this as row 0, 1, 2, 3, 4, 5, 6, 7. Well, it's just that second number there. If you add the squares of each number on row R, you get the middle element on row 2R. So for example, on row 2, the sum of the squares is 1 plus 4 plus 1 is 6. That's the middle element on row 2 times 2 is 4. The sum of the squares on row 3 is 1 plus 9 is 10 plus another 10 is 20, and that's the middle element on row 6, 2 times 3. And that always holds for some reason.
Are most of these something like proved or just somebody figured out but there's no proof for them? They're just correct for me.
I think they're all proven.
Proven?
Yeah.
Even the 11 powered up row?
Yeah, I think so. But I don't know the proofs. I can envision the proofs for some of these, but I haven't seen them. And the other one that I mentioned was 11 to the 0 is 1, 11 to the 1 is 11, 11 squared is 121, 11 cubed is 1331, 11 to the 4th is, I think, 14,641. And when you get to 11 to the 5th, it would need to be like 1, 5, 10, 10, 5, 1, and that's not a valid digit, 1, 0. But if you treat that accordingly,
It does work.
it works.
No, I think
When
it
you get up to where you said?
When you say the sum of x squared on row R, do you mean everything summed up?
Yeah, sum of each of the elements on that. Well, what's 11 to the 5th?
161051.
Right, so this is a 10, which is a 0, and you carry the 1. 10 plus 1 is 1. Carry the 1. 5 plus 1 is 6.
Okay, I got
That kind of thing. Yeah. Which means if you work like base a million or something, then I think the pattern holds really nicely for a lot more rows.
Can you have an infinite base?
That's an interesting question.
Because I mean, in that case, if we had an infinite base, are we not just talking about an array of numbers?
Yeah, if you have an infinite base, you have a separate symbol for each number, which is somehow like more equitable. It's like the social order that you would like.
You could take an infinite base represented in base 10, which would be basically what you're doing there, but
Right.
each 10 is, for example, like I said, just an index and not an index, a value.
Yeah, but I don't think you can square a number in an infinite base using an algorithm, just like you can't square 2 and find out that it's a 4 using an algorithm. You need to know that the symbol 4 means.
Right, but what if we represented that infinite
Yeah.
base in base
It
10?
makes you wonder how you would create an infinite base like that, and I think my brain automatically goes to each number's symbol is representative of its factors.
It's not, yeah. Oh, yeah.
There's a certain number of ticks for each.
Yeah. That's a cool question. I'm gonna think about that.
But then that would make factorization very easy because
Yeah.
you can see what the symbol is made up of.
Well, everything will maybe be prime.
I mean, representing it is an interesting topic, but I'm wondering what the applications of that would be.
Yeah.
Would it not literally just be an array of numbers? Because that's what it seems to hold as.
Yeah.
Wasn't base anything just talking about representation anyway?
I think so.
Yeah, that's all that it really comes down to
True.
is when we restart the clock per se.
Yeah. Right, it's using a smaller set of symbols than the set of numbers you care about, so we take ordered combinations of those symbols to represent extra things. There's an ungraded homework question. See if you can figure out what an infinite base number system looks like. And
Oh,
That's interesting.
ungraded.
well, fame and glory though, right?
I still think it's a component of its factors.
You're all under 35, right? So you can still get a Fields Medal in mathematics. So
Well, you have
there
to
you
be
go. I think you have to be under 35.
I'm gonna have to do it now. Under 40.
Can we phone?
40? Oh, they raised it maybe.
Can we phone a friend?
We were, yeah, right. We were like counting down the years in grad school. It's like, oh, too late for me.
I would say that my very quick Google search is not finding.
Infinite base.
No,
Yeah.
I'm looking at positional notation, which is bases, and I'm looking at some forum posts, and none of them are referencing this exact topic.
There's a lot about the Disney Infinity base, which apparently Google thinks is the same thing, but that's not.
It's like, what's this called? Oh, no, I know what you're
Yeah.
talking about.
It's going to get philosophical really quickly, I think, because we're sort of throwing away our basic way of like,
Categories and numbers.
yeah, and we're sort of working without categories. That's interesting. It's definitely one to think about.
Oh, God, I'm thinking about what rational numbers would look like in
Oh.
that system. It would get very,
Yeah.
very ugly. And the rails would be downright.
How would you even?
Yeah. Seems to be fair, the rails, you go, wait, no. Thank you, you've started a new obsession.
Good. All right, so let's talk more about recurrence relations. And this will feed into some of this, but hammer on the homework and bring more questions. I'll probably do a quiz not this Friday, but the following Friday on pigeonhole principle, counting, product rules, sum rule, combinations, permutations, that stuff. But let's get the homeworks done and turned in. I'll grade those, hand them back. We'll talk about them. We'll probably do it the following Friday. Will be another quiz. And I'll try to do a third quiz sometime before the final.
It's just one midterm, I suppose?
One midterm, one final, probably 3 quizzes, 3 programming assignments, some homeworks. So I might be spelling this wrong. A recurrence relation is a rule for defining
That's right.
Yeah.
each term of a series. I ended up using the word term 3 times, I don't want to. I say each term in terms of the earlier terms, and that's weird. So, a rule for defining each term of a series from those that precede it.
Didn't we already do this?
We did. We're going to do it some more.
Oh, okay.
All right, so we did this for things like n factorial and
Now we're
stuff.
gonna count it.
But we're going to count it. We're going to come up with formulas for it too. For example, bacteria population. So we'll start with that tomorrow, and we'll go from there to rabbit populations and bit strings and fun stuff like that. All right, so we'll start with that tomorrow. We'll go through some recurrence relations. We'll give some examples, and then I'm probably going to shift gears, and we're going to talk about Boolean things. Kind of a 250 refresher. George Boole's 200th birthday today. Google Doodle. Check it out. It is, and they've got a good doodle.
I just see the other day.
invent everything that's like Boolean?
I think it's,
So what?
Boolean?
Yeah.
yeah, it's just day to day.
Yeah, it's just
Well, on my phone it was.
Was it yesterday?
That looks fancy.
Maybe it's not up here yet, this was in UK.
I'm seeing it right here, /doodles /George -200 works. It's all in plain English.
Yeah.
Google.com
Yes. Yeah, I said go ahead and put some print statements in there and see the value of the variables. Okay. And that will probably take you to the right answer. All right.
But Fred, they talked to him.
So we're in base a million.
Yeah.
Pascal's triangles still look the same, relatively. 11 would be so
That's true. So probably the powers of your base plus 1. Maybe. 'Cause I don't know what's magic about letters in there.
yeah, that's what's making me think that's kind of weird because I'm always really hesitant to think anything about base 10 things are special.
Right.
And that almost seems like something about 11 is like has like a relationship to Pascal's triangle.
Yeah. You should be able to do like base 20 or something. Or just X.
Yeah.
Base plus 1. So yeah, try to.
Fair enough.
Yeah.
Did you have a certain day you wanted to see that movie?
We were talking Friday, right?
This Friday?
Yeah.
Okay, after lab?
Yeah.
Okay. That sounds fun.
If that works. Got horrible reviews.
Really?
Yeah. Steve Jobs.
Was it worse than the last one? I thought the last one had bad reviews.
I don't know. It's always good popcorn, though.
Alright.
All right.
See ya.
See ya.
So answer to your comment. which I
Yeah,
saw.
I got it.
Okay, did they actually upload the file? Because I went and attached the file to it, and I didn't know if it actually attached. I couldn't see it after I sent it.
I think I
And
got
I
it in
can
your note.
email.
No, I think I got it in your
Okay,
Yeah.
yeah. Sorry for misunderstanding.
All right.
It's just real quick.
Yeah.
So this is with Slack, if you're just using this thing prepared.
Okay.
This is with the string. Just read the entire string.
Okay.
I'm sure it would kill you in time if you had a really long bunch of strings, because it's going through the entire ring.
Right,
Every single
right.
element. I'm sure
So
time
that's
wise.
basically for doing numbers, right?
Numbers were alphabet. So if I were to have A113 and then A114, it goes through the entire string. And then like A112.
gotta go to class. Get out of here. So we'll put these in.
Yeah, I'll put them all in
What?
alphabetical.
It would put them in this order. That's cool.
It's actually going through the entire string.
Yeah.
Instead of saying, you know, if I have one here saying it's equal to everything else is okay. Whereas this, I have a 50% overall. And next it tells me just something that's null or not.
Well, this will move until it finds something not equal. 50%. The problem is that you still need to. Apparently, I still might be able to
Apparently, I still might be able to act. Yeah, same here. I think I can. I think I can.
I know it's ridiculous.
That's STR. All right, now.
Test today? On what? Is it on BI? Yeah.
That's cool.
I couldn't even study.
Yeah.